This is our third QQT from Unit 1. I've drawn some of this because I don't want to do it freehand. It's bad enough when I had some time. We've got a block on a spring with a rough surface. A block is initial at position x equals 0 and in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from position 0 to x equals negative d, as shown above, compressing the spring by an amount delta x equals d. The block is then released. At x equals 0, the block enters a rough part of the track and eventually comes to rest at position x equals 3d. I think I put that in Canvas. Hopefully you picked that up. The coefficient of friction between the kinetic friction between the block and the rough track is mu. So on the axes, we're going to sketch and label graphs of the following two quantities as a function of the position of the block between x equals negative d and x equals 3d. We don't need to calculate values, but the same vertical scale should be used. So my kinetic energy here is in red. I probably should have indicated that. So kinetic energy has that sort of concave down curve that you see. Kinetic energy is going to be 0 at negative d when the block is released, and it's going to increase while the spring is acting on it, and it's going to be at a maximum at x equals 0. Right? Now, I know that's kind of contrary to what you're thinking, because when a block oscillates, that is also when it has its maximum energy, but don't get those two things confused. What happens after x equals 0 is that the kinetic energy decreases. The friction is going to do work on that block. Work is equal to the change in kinetic energy. So this is a linear function. So the kinetic energy has that sort of concave up between d and 0, and then the linear between 0 and 3d. Now my potential energy is in green. So potential energy starts at a maximum here, right? The spring is compressed as much as it's going to be compressed. And so that's going to decrease in value between negative d and 0. And so what I tried to show here is that these aren't straight lines. They're curved. And you've seen this in your book, and we can do it in person if you'd like. They're not curved, but what is important is that the total energy stays the same. So I've tried to make that on the graph to where they actually do meet up like that. Then you see once we get to x equals 0, the green line is at 0 there. So let's talk about the 4 points for that. 1 point for either energy curve with a reasonable shape between x equals negative d and x equals 0, with max and 0 values in the right places. Okay, so again, we haven't indicated any values here, but this is obviously the maximum value and 0 is already posted there. So 1 point for either energy curve. 1 point for two energy curves between x equals minus d and x equals 0, such that the total energy is constant. Even if the curves are wrong, if you can indicate, and you can even do that explicitly, that the total amount is equal, you can get that point. 1 point for the potential energy being 0 from x equals 0 to x equals d. The spring has lost contact with it. There's no change in gravitational position, so it's 0 from x to 3d, And then 1 point for kinetic energy being linear from x equals 0 to x equals 3d, and for ending at 0, its final value, because the block comes to a stop at 3d. So that's 4 points for part A. All right, now we get to practice a little bit of factor of change. If the spring is now compressed twice as much to delta x equals 2d, a student is asked to predict whether the final position of the block will be twice as far. The student reasons that since the spring will be compressed twice as much, the block will have more energy when it leaves the spring, and it'll go twice as far. So, which aspects of the student's reasoning are correct and which are incorrect? So, it is correct that it will have more energy. Okay, the block will have more energy. So that's the qualitative part of this. But as we've learned from painstakingly doing the factor of change questions, just because that doubles doesn't mean everything else is going to double. Okay? So the student is wrong to say that the new energy is going to change the final position linearly. Okay? And that is because the distance doesn't necessarily depend on the amount of energy coming out of the spring. So it's correct there, incorrect. for assuming a linear dependence. All right, and as you guessed it, we're gonna dig into that in part C. Using quantitative reasoning, using equations as needed, we're gonna develop an expression for the new final position of the block. So what we have here is 1/2 kd squared. And I'm going to change this to 1/2 kx squared because that's what we're most used to. All right, that's equal to 1/2 mv squared. And so that's our initial kinetic energy, number one. Now, if I double, right, if I double the position, all right, double the amount that the spring is compressed, we get a 1 times a 1 times a 2 squared, which is equal to 4k1. So what we're told here is that double the delta x, we quadruple the kinetic energy. Now, once we're in the rough section here, right, we have delta K equals the work done by friction, okay, the force due to friction times the D. And I probably should call this capital D because that's what we're doing here. Now, we know the change in kinetic energy, we're going to end at 0. So delta K is really equal to K, right? So if my new K is 4 times the old K, then my force of friction is not going to change because the block is the same. And then we have our D here. So our new D is equal to 4 times the old D. So we're really going to go to 0.12D. And this was a little confusing because they're kind of calling the points D, but what I want you to get out of that is doubling the compression quadruples the kinetic energy, quadrupling the kinetic energy quadruples the distance. If the distance was 3D, now the distance is 12D. So that was a little bit unconventional there, but we get 1 point for saying that the new kinetic energy is 4 times the old kinetic energy. 1 point for realizing that the friction remains the same, and 1 point for equating the initial energy to an expression that shows the energy dissipated by friction is proportional to the distance that the block slides down the rough track. So I would say 1 point for realizing the new kinetic energy there, 1 point for realizing that the friction remains the same, and then 1 point for realizing this functional dependence on kinetic energy. Then part D finally says, explain how any correct aspects of the student's reasoning identified in part B are expressed by your mathematical relationships in part C. Explain how your relationships in part C correct any incorrect aspects of the student's reasoning identified in part B. Refer to the relationships you wrote in part B, not just the final answer you obtained by manipulating those relationships. Okay, so what we realized was correct was that an increase in compression results in an increase in kinetic energy. So we realized that that was correct. But by using our factor of change method here, we corrected the part of his reasoning where we said it would be a linear relationship. So by realizing that we quadrupled the kinetic energy and that the kinetic energy and the distance had a linear relationships, that's how we corrected that. So here's the rubric that they give. 1 point for saying that the student was correct by saying that the block has more energy when compressed more. Okay, we verified that. 1 point for saying that the student was correct that the work done must be more in the second case. So the work is more, okay? But then 1 point for realizing the student is wrong to say that that distance compressed is related linearly to D. It's actually D is related to x squared. So hopefully you could find your way through that rubric.